Okay, good morning, everyone. I am going to get started because we're a little bit behind on our syllabus schedule, and it's okay, but I want to keep moving along. So I'm going to have a couple of announcements, or not really an announcement, I'm going to describe the term paper instructions a little bit. Those are already posted on Canvas, but I'm just going to go through and see if there are any questions too, since you also should be getting started on that assignment. And then we're going to finish up our discussion about mechanical properties of materials, specifically talking about fatigue. That's our last topic, thinking about mechanical properties. And then we're going to move into some actual properties of polymers and how we can classify them and how we can describe them. And those will be terms that I will be using the rest of the semester. So kind of a introduction to polymers vocabulary lesson. Okay, so for the term paper, again, these instructions are posted on Canvas already. I've also posted a grading rubric, so you know what I'm going to be looking for in each section. And I have the number of points broken down by each section of the report and a guideline as far as the length of each section as well. So these are not strict guidelines. Obviously, if your introduction section is longer than one page, for example, you're not going to lose points for that. So the page guidelines are just that, they're just a guideline. But the number of points, obviously, by section is what I'll be following when I grade these. So do pay attention to that. Do remember to include each section. If you leave a section out, you will automatically lose those points. So do pay attention to the instructions and follow them closely. The final term paper that you're going to submit is between 10 to 12 pages. I like 1.5 spacing. You can use double spaced if you want, but you may find that you need to reduce it to 1.5 spacing to include all of these categories. So 1.5 to 2 spacing is what I would recommend. 10 to 12 pages. I won't read past 12 pages. So 12 pages is a hard stop. And if you can certainly submit something that is 10 pages, or I guess you could submit something that's less, but you're probably not going to have enough detail to cover all of these sections if you submit something shorter. So those are my guidelines, but the 12 pages guideline is firm. I won't read everything on the slide here, but I'll just kind of give you an idea of the sections that I'm looking for. You need to introduce your device with a short description, list the materials that you're going to be focusing on. So the assignment is you've been assigned or you've chosen a medical device. You and your partner together are going to choose 2 materials from that device to delve into and tell me a lot about. And so usually the way that partners divide it up is for each partner to take one material and focus on writing that section of the report, and then split up the other sections however it seems fair. Obviously, you don't have to follow that, but just a suggestion that the way a lot of people split this up. So you introduce your device, list the materials that you're going to be focusing on in your paper, talk about service requirements, performance requirements, how is the device used, what do the mechanical properties need to be like, since we've just talked about mechanical properties. What do the chemical or the surface properties need to be like for this device? How long is it used in the body? Is it, if it's degradable sutures, it's going to be a matter of days. If it is a hip implant, as long as possible. Most implants, as long as possible, I would say, is the lifetime requirement. And then for each of the 2 materials that you select, this is going to be the bulk of your paper discussing these materials details. You're going to come up with the following information for each one. Basic characteristics is the first bullet point here. So you do not need to tell me the specific gravity and the viscosity and the molecular weight. You don't need to tell me all of this information for your material, because that's just going to take up valuable space in your paper. Like I said, I think you're going to probably be wanting to cut down the information you have to get under the page limit rather than struggling to meet it. So just tell me the characteristics of your material that are interesting or that are relevant to the function that you're describing, relevant to the device that they're a part of. So if molecular weight is relevant to that, for example, If you were looking at the cup in a hip implant, the socket basically is made of ultra high molecular weight polyethylene. That's actually the name of it. And why is it ultra high molecular weight? Well, that helps it serve its function in the hip implant. It's resistant to wear, it's resistant to breaking down. So that would be an example of a characteristic or a device where molecular weight would be an important thing to mention there. Discuss the manufacturing process a little bit. Mechanical, chemical properties, again, only really limit this to properties that are relevant to your device, to the design, to the function of the device. And I have in yellow text here, which means it's important to discuss the structure and function relationship. What do I mean by that? Well, when I say structure, I'm talking about the chemical structure. How are the atoms connected? How are the molecules connected? Covalent bonds probably, but what type of functional groups are on your polymer and how do those translate to favorable properties in your device? Surface properties, chemistry, mechanical properties, that sort of thing. So we talked in the mechanical properties section about what connects the chain backbone and then what connects the chains to each other. And the strength of the forces or the strength of the interactions between polymer chains, one to another, is going to underlie the mechanical properties or be able to explain some of the mechanical properties that we observe. So that's what I mean about connecting structure to function. Connect the chemical structure and the connectivity of the atoms to the function of the device and the function of the material on the bulk scale or on a scale that we can observe with our eyes. Okay, so do make sure to connect those two things in your paper. There's a question here. Someone says, can we use images on the term paper to depict the chemical structure? Yes, for sure. You are welcome to include figures in your paper, but they are going to be included in the page limit. So you don't have to include figures if you don't want to. I would be a little bit conservative with figures just because you don't want to take up your page space with those. But you know, they say a picture is worth 1,000 words. So if you really think your picture is worth 1,000 of your words, or 100 of your words, that's the space it's going to take up in the paper. Go ahead and include it. Make sure that you refer to the figure in your text somewhere, say see figure 1 or something, and then give your text, give your figure a label, figure 1, and a short description telling me what it is. Okay. Also discuss the medical grade, manufacturers, kind of some market information if you can get it. I know market analysis reports are pretty pricey, so don't spend $1,000 plus on a market analysis report. Just find information that you can. A lot of times if you call up a supplier or a manufacturer, they might give you information on the cost of the item. So do your best to get a hold of that information. You can let them know that this is information for a school project. Sometimes manufacturers will be less than forthcoming with cost of materials. But if you tell them, kind of disarm them, just tell them you're doing a school project, writing a paper, they'd be more forthcoming with information. One more chat question. Someone says, let's see. Okay. Raul, if you can ask me that question at the end, question about the lab, please remind me at the end and we can discuss.
All right, sounds good. Didn't mean to interrupt your lecture.
No worries.
Professor?
Yes.
I had a quick question about the progress report.
Yes.
I know last class you said it was due on the 20th, but on the syllabus it says it's due on the 22nd. So which day do we follow?
Let's see. It should probably be next Monday, the 20th.
Okay, thank you.
Mm-hmm. Yeah, let me correct that. Yeah, I'll check that. Progress report 1. Sorry about that.
Do we have to create them ourselves, or can we use it but then just cite it?
Create what?
For the figures, if we choose to include them in our paper, do we have to draw it out on a tablet ourselves, or can we use it and then cite it from some other source?
Oh yeah, definitely. You do not have to create it on your own. You can use it from another source. Just make sure you cite that source.
Okay, sounds good. Thank you.
Mm-hmm. Yeah, so figures can add a lot, but just watch that you don't have too many taking up too much space. And then finally, the last section, second to last section of the report, we want to discuss any risks of the device or safety issues. For instance, how does your material fail? Is it prone to fracture under bending, like a ceramic would be, or something like that? We want to discuss that in your paper, and specifically how that material contributes to the risks of the device, risk of failure or risk of degradation, that sort of thing. And then the last section of the paper is the acknowledgement section. Sometimes people get confused and they want to acknowledge me as the professor of the class. That's not what it's for. It is so that you and your partner can work on splitting up the work equally. So I want you to tell me who did which sections of the paper. And hopefully that will help you come to an agreement and splitting things up as equally as possible. So if you don't contribute equally with your partner, your points will be, what's the word? You won't receive as much credit as your partner, or you won't receive equal credit. You can receive a different grade from your partner if I don't feel like you contributed equally. And I'm a little bit lenient with that, but it's usually possible to tell if one partner did 75% of the work and the other only did 25%. That's a case where I would maybe give different scores, but if it seems pretty balanced, I'm going to leave that alone.
Yeah, but what are some factors that we can tell whether if each person is doing it equally or not, even though without looking at whether who did what? How can you tell?
Well, I mean, yeah, there's no like hard guideline. I'm not going to say like, oh, this person did 55%, this person did 45%. It's not like that. Like I said, it's usually possible to tell if someone just was not pulling their weight. And in that case, I might try to talk to you, or sometimes people talk to me before the assignment's even submitted if they're having problems. But that's what the acknowledgement section is for. Just it shouldn't be a problem for most people. Hopefully it won't be a problem for anyone in this class to have equal contribution, but don't stress about it. It's just there for you if you're having problems, basically.
But then sometimes like partners, they work on sections together. You know what I mean? Like it's not.
That's fine.
Okay.
If you both work on the section, then just put both of your names on that section.
Okay.
Totally fine. Someone's asking if the acknowledgement is part of the page count. No, it is not. Acknowledgements does not count on your 12 pages, and neither do the references. So actually, I didn't state that at the top. Acknowledgements don't count. It's a short section anyway, but it doesn't count. References don't count. So cite as many references as you would like. Please, I don't want to restrict that at all. Okay, any other questions? I think I have one more slide on term paper. Oh, two more. Okay, as I mentioned before, the page limit is strict. There's a lot of pages and a lot of groups, so I won't grade past 12 pages. So make sure all of your sections fit within that limit. I posted a document called the BME Style Guide, which is maybe not as exciting as what a BME Style Guide you would think it is. It's a formatting and writing style guide that's available on Canvas. So take a look at that to see how we do section headers, how we format references, and that sort of thing. You must cite all of the references that you use and rephrase them to avoid plagiarism. There's two parts. You have to cite and you have to rephrase. It's not enough just to cite. I think I mentioned before, the website references are okay as long as they're from high quality sources such as professional organizations, ASME, BMES, government websites, or companies that make these devices would be examples of high quality websites. You have to have at least 20 references. And I highly recommend using a reference management software. Wait 1 second, just going to mute someone. Reference management software will keep you from crying if you have 30 references in your document and you find one more reference that you want to insert in your document between references 19 and 20, for example. It will automatically renumber all of your references after you insert that citation and save you from having to go in and change all of the numbers after 19 in your document. It also does all the formatting for you as long as you set it up properly. So it can save you a lot of time and headaches. So do check that out. A lot of people like PaperPile. It works with Google Docs. I'm not sure if these others work with Google Docs or not, but PaperPile does. There's a free version. RefWorks is available through our library for free. And then these two, Zotero and Mendeley, are services I've used. They're also free, and you can get them as an extension for Chrome, where you're on a web page. There's a paper that you're reading. You click a button on the little extension button, and it downloads the PDF for you and saves the papers in a library. You can add tags, you can highlight things, and it will save all of those annotations. So very useful software for free. I would highly recommend checking out one of those. It'll come in useful for 198 too. If any of you are in 198, highly recommend you find some kind of reference management software to work with. Okay, and then I wanted to talk about something called block quotations, and please don't do it. A block quotation is when you take a quote from another source that is 3 or 4 lines long or longer. Really, there's no reason to have a quotation at all in a scientific or technical paper, but a lot of times students use this. A lot of times I see it in the manufacturing section when they talk about how their polymer or the material is manufactured. And they either don't understand the manufacturing process or they don't want to take the time to paraphrase it. And so they will just copy directly a paragraph from another source and just put quotation marks around it. So do not do that. Not acceptable for scientific and technical writing. You may see this in your English literature classes if you're taking any classes like that. It is acceptable in those types of classes to do a block quotation, because you might quote Martin Luther King Jr., for example, and then comment on what he said. But for this class specifically, do not do this. You need to paraphrase the material, rearrange the words, write it another way. If you're having trouble paraphrasing the material, you probably need to find another source that talks about that manufacturing process. And then you can kind of combine the information from those 2 different sources, because they're going to say it 2 different ways. So just a final warning about plagiarism. If I find copied text in your paper, even if you've cited it, if you've not paraphrased it, you'll get a score 0 for that section of your paper. So, or if there's a block quotation, you will have a 0 for that section of your paper. So please put in the time, allow yourself enough time when you're writing to think about things so that it's easier to paraphrase. If you're in a rush at the last minute, it's much more tempting to plagiarize. It's much more tempting not to rephrase, and you may not be able to think so clearly if you're rushing to do the assignment. So starting in advance will help out with this. And folks always ask me, what is copying text like? What if I copy 3 words in a row that's the name of a process, like scanning electron microscopy? Obviously, there are that is a term. You're allowed to use terms like that. But I would say if you're using more than like 5 words consecutively from the same source, you probably need to find another way to say that. And if you have trouble with that, if you have a specific example, definitely see me in office hours and I can help you work through that. Okay, so on to the actual material for today, talking about wrapping up our section on mechanical properties of polymers and then starting to develop our vocabulary of polymers as biomaterials. Whoop. Okay, so we're going to finish up mechanical properties with talking about fatigue and how fatigue causes failure in polymers. How do we assess fatigue? We're going to look at a fatigue test and then something called a fatigue curve, an SN curve. And then we're going to jump into our discussion about building vocabulary around polymers. So talking about how polymers are put together using monomers and how we can predict things about polymers properties by knowing their crystallinity. So fatigue is a topic you all know about, I'm sure, the stress of college. But we're talking about material fatigue here. Materials can get fatigued too. And fatigue is something that happens when you have a material that's repeatedly exposed to stress. If a material fails after one exposure to stress, that's not called fatigue failure. That's just failure. Fatigue failure is what happens when you're loading and unloading a material many, many times. This happens a lot in implants in the body. For instance, a hip implant. You can think of the stress cycles, the loading and unloading on that joint. Every time you take a step, every time you walk, you're loading and unloading that joint. And so that material would be subject to fatigue or fatigue failure over time. So chat message. Rahul asks if you need to submit the first progress report individually or one submission per group. One submission per group is fine for that. Okay, so fatigue failure happens when you load and unload something over time. There are lots of cyclic stress applications in the body, aside from walking. If you've got a vascular graft, basically a substitute blood vessel that you're implanting, obviously that's going to expand and contract with every heartbeat. If you've got a mechanical heart valve, that is going to undergo cyclic loading and unloading from the blood flow that's coming past it with every heartbeat. So there's two sources of fatigue. There's what's called thermal fatigue that can come from heating. That's less relevant to biomedical applications because we really don't deal with high heats in the body. But it's a possible contributing factor. But more likely, the cause of fatigue in biomedical devices, and specifically implants, is mechanical fatigue. So we're going to look at how mechanical fatigue initiates and propagates through the material to cause failure. Mechanical fatigue can depend on a number of different properties, both the material properties and the mechanical properties. And it often initiates because of a defect in the surface of a biomaterial. So I've mentioned before that for most biomaterials and most implants, the surface properties are just as important, if not more important, than the bulk properties of the material. You need bulk properties for mechanical strength. Hopefully they prevent, they don't creep and that sort of thing. But the surface needs to be relatively smooth many times to prevent fatigue failure. So if you've got a little crack in the surface of your device here, for instance, this picture that it's on the slide on the right here, there was a little surface scratch or a crack or something like that right where I'm pointing the mouse. And over time, that crack grew and propagated until it led to failure of this material, this polystyrene, sheared off completely as that little defect propagated. So that phenomenon, or these little defects, when they occur on the surface of a material, and the material is subject to repeated loading and unloading, those are called stress raisers, meaning that the material is undergoing a bulk stress that we would measure on a stress strain curve, but the presence of these little defects or cracks in the material are going to increase the local stress or force felt by the material at that location. So this is a poorly drawn little MS Paint picture here, but it kind of illustrates the point. This white triangle is meant to depict a crack or a defect in the surface of a material. And this crack acts as a stress raiser. So even though there's a certain stress or a certain force that's being applied to our biomaterial, in the vicinity of this little crack, the stress felt by the material is actually much higher. That's called a stress raiser when that happens. And so if you can imagine there's a high stress here, if you're loading and unloading this material many, many times, this crack will propagate and widen or lengthen until it can propagate, eventually propagates all the way through the material, and then you have failure of the material. So a tiny crack or a tiny scratch in the surface of your device can over time lead to failure of the whole device because of this phenomenon of a stress raiser, raising the local stress above the stress that you're applying to the whole material. Okay, and so this is kind of what the surface of a fatigue failed polymer might look like. This area is where the initial scratch or the defect was, and then that crack propagated all the way through the material until it failed. And so fatigue actually looks like a fracture of a brittle material, such as a ceramic. rather than a ductile material. Many polymers fail this way as in ductile fracture. As you may have seen in the lab when we were pulling apart the dog bones, they kind of they get thinner in the middle. They undergo this phenomenon called necking, and then they will fail and pull apart. With fatigue failure, because you've got a crack that's slowly propagating across the material, it's going to fail suddenly, and it's going to fail all the way across the material. It will break apart. And that occurs because the stress in fatigue failure, the stress that we are applying to the material is less than the yield stress. If it was greater than the yield stress, we would probably have this ductile fracture type of pattern. But because we keep the stress under the yield stress, which we should, and we are cycling, loading the material and unloading it over and over again, we eventually get failure, but that failure happens when we are lower than the yield stress of the material. And so our fracture pattern looks different. Okay, so first clicker question here, based on what we just talked about. What do we not need to have fatigue failure? Which of these 4 options? Okay, and most of you said C, which is correct, very high tensile stresses. Someone tell me why we don't need high tensile stress in order for things to fail.
Well, because if the tensile stress is too high, then they'll make it plastic, and fatigue failure does not apply for plastic. It only applies for elastic. When it says elastic, you mean before yield stress.
Yes, yeah. So we should always be operating when we're using a medical device or any kind of material. We should always be operating under the yield stress of the material, unless for some reason you want your material to deform for the application. So we're always operating under the yield stress, especially for a situation where you have to do repeated loading and unloading. But that even the low yield stresses, even a low applied stress can translate to something that is locally higher than the yield stress because of stress raisers. And so when it's higher than the yield stress of the material, obviously the material starts to fail little by little. That crack propagates until we get catastrophic failure, catastrophic rupture of the device. Good. Okay, so this slide here is just showing how different types of shapes or different types of defects or cracks in your material will give different stress distributions. So for instance, if you have a hole in your material, that the stress felt around the area of this hole of the material can be up to 3 times as high as the stress that you're applying to the rest of the material. So a hole is concentrating the stress as well. The stress around a crack, like we drew before, can be up to 8 times higher than the stress that you're applying to the bulk material. So why does this matter? Well, it's good to know if you are designing a material that is going to be subject to repeated loading and unloading. You need to minimize the presence of cracks and defects on the surface of your material to prevent seeding sites or nucleation sites for fatigue failure to occur. Sometimes it's unavoidable. I mean, you might need to have a screw hole in your part. For instance, if you're making some sort of assembly, you're going to need to have little maybe slots or holes in your device. But it's good to be aware that those holes and slots can be stress raisers and can be potential points to promote device failure, particularly under fatigue. So if you're designing a device, you want to be aware of this phenomenon of fatigue can potentially happen. You probably want to do some calculations to figure out, or some simulations to figure out what the local stresses would be around those areas, so that you can keep the applied stress to the device lower than the yield stress, even in those areas, and try to prevent fatigue from occurring. Try to prevent failure from occurring, I should say.
I had a quick question.
Sure.
So, what you were saying just earlier, if basically if the material fails under the yield stress, does that imply it's most likely brittle then?
I guess that was a misnomer. Let me go back to that slide. So the words ductile and brittle here don't necessarily describe the relative ductility, because we talked about ductility as being the elongation before failure of the device. So I wouldn't necessarily, you could have the same polymer be in the same polymer at the same temperature. If you load it at a high stress once, you might get a ductile fracture. If you take the same material and the same temperature, but you have different loading conditions, so now you're loading at a lower stress, but you're doing cyclic loading, you would see that same polymer fracture in a brittle fracture pattern. So, so when we're doing fatigue testing, we are going to be using a materials testing device, the Instron, similar to what you used in the lab. And you're going to load and unload the material many, many times, and you're going to be testing the device to the point of failure. So the test that you run is the same as for a regular type of mechanical test. You would do a tensile test or compression test or bending test even, but you would load and unload the material for thousands of cycles. And the data point that you're trying to get is failure. How many cycles until failure? So fatigue tests, as you can imagine, take a really long time to run. You got to run a material until it fails. And then you get one data point from that test. So whether it fails at 10,000 cycles, 50,000 cycles, whatever, that could take days. That test could take days to run, and you get a single data point from there. The other thing that complicates fatigue testing is that fatigue failure is very variable. And you can think about why that might be, because we talked about what causes fatigue failure. It's the presence of little surface defects, cracks, and things like that, which are different from device to device. If you've got 10 devices and you do fatigue testing on all of them, some of those devices might fail at only 10,000 cycles. Some of them might fail at 100,000 cycles. It's going to be a very broad distribution. So to get good fatigue testing data takes a long time, takes a lot of samples, because you have to test all the way to failure of the device, number one, and two, because the defects or the cracks that cause failure can be different from device to device. So how do we account for this? How do we plot the data for fatigue testing? We use something called an SN curve. So S is for the applied stress, that's on the y-axis, and N is the number of cycles. We plot the number of cycles that it took to fail the device given a certain applied stress. So if you've got 100 samples maybe that you want to do fatigue testing on, you would subject some of those samples to maybe applied stress of 40, applied stress of 60, 80, 100, different values, test them to failure, and record the number of cycles it takes to reach failure for each of those stress levels. And you would obtain a curve that looks sort of like this. So this one is not for polymers, this is for steel and aluminum, but the point is the same here. And there are a couple of vocabulary terms associated with fatigue testing, which is what these few slides are intended to describe. So the first is fatigue life. Fatigue life would be how many cycles it takes until the material fails, given a certain applied stress. So as we increase the applied stress, the fatigue life, or the number of cycles to failure, is going to get shorter. You can see that as you move from right to left on the plot. So fatigue life gets shorter, number of cycles to failure gets shorter as we increase the applied stress. And that makes intuitive sense. So I'm going to move to the next slide now, which the title says question. This actually might not be on the PDF upload, so I'm going to skip that one for now. I'm moving to the next slide, which is fatigue testing, the SN curve. And I'm asking a question here. And I say, results of the fatigue test exhibit large variability, and I'm asking why. So can anyone tell me, why do you think fatigue tests would exhibit large variability in the results?
Well, because the results may be inconsistent due to many factors like defects.
Yeah, exactly. Yeah, the cause of fatigue failure is those surface defects, and kind of by definition, defects are different from sample to sample or from device to device. And so we're going to get different fatigue life for each of those different devices. Excellent. Okay, moving on to the next slide, where I've got the term endurance limit highlighted in yellow text there. So this is another term that's associated with fatigue testing. Some materials may have what's called an endurance limit, where they are able to withstand repeated loading and unloading of cycles to infinity. In theory, you could unload and load that sample infinity times and it would not fail. In practice, obviously, eventually the material would fail due to entropy, but you reach the end of your fatigue testing, the maximum number of cycles that you want to test, and the material does not fail. The applied stress that is associated with that point of non-failure of the device is called the endurance limit. So visually, you can see on the curve here, the curve flattens out or levels out. And so when the portion of the curve at which it flattens out is called the endurance limit of that material. So we can describe materials as having an endurance limit. We can describe them as having a certain fatigue life given a certain stress level. So those are terms that you should be familiar with for describing the results of fatigue testing. And I'm going to jump ahead to the slide that's titled Polymers as Biomaterials and start that section. So the next slide, I'm showing some examples of polymers that we have in medicine. You can probably think of many more examples. One of the topics of your term paper are examples of polymers in medicine as well. Metals and ceramics are certainly used still for biomedical applications, but by far polymers are the most common material class that are used for biomaterials because they have such varied properties. They have tunable properties, and it's just such a broad category of materials. So down in the lower left corner, I have an image of a hip implant, and this is a good example of biomaterial where polymers can't do the entire job. We still use metals for hip implants. We still use ceramics for some bone applications. But polymers have a role to play in hip implants as well. This little cup or this little liner that goes in the hip socket is made of ultra high molecular weight polyethylene. That's what this acronym is under here, UHMWPE. And that gives certain properties that allow the ball to move around in the socket very freely and very smoothly. So polyethylene is used in that application. Moving toward the center of the slide, there's a picture of some sutures there. And there are many different types of sutures made of polymers, but the ones that I'm showing here are degradable sutures. So you may have had these in the past before if you've had surgery. If you don't have to go back to have your sutures taken out, most likely they were degradable. These ones are made of a polymer called PGA, polyglycolic acid, which we'll be talking about in great detail during our degradable polymers lecture. So obviously the ultra high molecular weight polyethylene that I showed first with the hip implant is a material that's designed to stick around for a long time in the body, as long as possible. And then degradable sutures, they're engineered, they're designed so that they degrade within a certain amount of time, so that they can kind of match the rate of wound healing. They're dissolving while the wound is healing, so they don't stick around any longer than necessary. If you've got materials sticking around longer than necessary in the body, you can create more problems with the immune system, trigger the immune system more than you need to. In the bottom right corner, I'm showing a material called bone cement. It's made of polymethyl methacrylate, another polymer that we will talk about. And in the top right corner, I have vascular grafts, basically replacement blood vessels, which can be made of many different types of materials. I have peat here, polyethylene terephthalate is one material. Another material, EPTFE, polytetrafluoroethylene, otherwise known, or AKA Teflon. You can make vascular grafts out of Teflon. And the E refers to the fact that it's expanded Teflon. It's sort of a meshwork of Teflon. So we can mold polymers into all these different shapes. We can engineer them with different properties, whether they're going to degrade or persist in the body. They can have all different types of mechanical properties. For example, they're just very, I don't want to say flexible, I want to overuse the word flexible, but they're very customizable to a particular application. They're very easy to manufacture and work with. They can be spun as textiles. They can be cast into shapes like this socket on the hip implant to suit the application, whatever the application may be. So I'm going to the next slide now called polymers as biomaterials. And you can see, I've mentioned many of these points before, that polymers are the most commonly used class of biomaterials, more so than metals or ceramics. They're ubiquitous in medical design. And polymers consist of very long chains of repeated elements called monomers or simply mers. And they can have molecular weights up into the millions, actually. When you took chemistry, you probably talked about some simple compounds, salt, maybe even some proteins that have molecular weights in the hundreds. Polymers can have molecular weights up into the millions since they're such long chains. The physical and chemical properties of polymers can be customized, as I mentioned. You can change their properties using chemistry and grafting things onto a polymer, for instance. You can also change the properties by the way you process the material, similar to the way you can change properties of metal or ceramic, the mechanical properties, by the way that you process them. Because we can tune the properties of the materials, we can make them match those of the tissue, native tissue in the body. Metals and ceramics generally have a higher strength than most of the materials in the body, and that can cause problems like stress shielding. But polymers are softer. Our bodies are softer. And so it's almost easier to match the mechanical properties of polymers to our native body tissues rather than metal or ceramic. Okay. Moving on to this next slide, which says, is titled Monomers and Polymers. Just to build some vocabulary here and get us all on the same page. If you are not familiar with these terms already, a monomer is the individual unit that makes up a polymer. They're also called just mers sometimes. And so I have two examples here. I've got polyethylene. And polyethylene's monomer is the simplest type of monomer you can have. It consists of 2 carbons and 4 hydrogens. It's shown there in red. That is called the monomer of polyethylene. And when it's actually in monomer form, so when it's not polymerized, there's a double bond between the carbons here, which satisfies the octet. And we'll talk about how monomers polymerize into long chains in a future lecture. But just be aware whenever you see a monomer, most of the time the carbon, there's a carbon-carbon double bond there. And that double bond is broken to form the polymer chain. So this is polyethylene. And then on the bottom, we have another example of a polymer with its monomer there. The only difference between these two polymers is that one of the hydrogens in polyethylene is replaced with a methyl group, a CH3 group, which gives it different properties. As you can imagine, the polymer on the bottom is going to be, the chain is going to be bulkier. So if we're starting to think about how we can predict functional properties of the material based on its structure, this is the connecting the structure to function thing. The polymer on the bottom is bulkier. So if you had chains of polyethylene and chains of this other polymer, chains of the bulkier polymer are not going to be able to pack together as tightly as those of polyethylene. So that's going to change the mechanical properties that we see from that material. And I'm going to stop here for today. And next time we will pick up and continue talking about properties of polymers. I will upload this recording as I normally do, as well as the slides that I got through today. And let's see, I can answer questions now as well. Someone was asking about lab, I think.
Yeah, my lab instructor still has not posted the lab manual for today, for this week, even though there's lab this week.
Okay, could you send me a private message with your section, or just tell me your section name or number?
My section is 4 and my instructor is Muskan. It's Tuesday from 12:30 to 3:15.
Okay. Okay, I'll see if they can send that out then. Thanks for letting me know.
No problem.
And then I will look at the homework due date too. I can push that out.
Homework due date is 20th, which just means next Monday.
Yeah. And there are questions about the degree of polymerization, which we didn't get to today and I expected to. So I can change that to I'll change it to next Wednesday for now. So I'll change it to the 22nd, give you 2 extra days. And that should give you a week from Wednesday, and we'll cover that material on Wednesday. Although the slides are already posted, if you want to get a head start on the homework, you can take a look at the slides that I posted for today's lecture, and you should be able to get a good start on the homework from those. But we'll talk about it for sure on Wednesday, and then the homework will be due a week from that date.
There's also something about like a weight average and a number average given molecular weight. I don't think it's in the slides. At least I can't find it right now.
Oh, I thought it was posted in today's lecture 6.
Oh wait, no, sorry. I think I found it. It's slide
Yeah.
24 or 34. But then I'm like confused what you do with like the X's. Is that N or is that M?
The X's. So N is the number of chains that have that molecular weight, and X would be like the fraction of chains that have that weight. So if there's 100 chains and 6 of them have a certain weight, then it would be X would be 0.06, basically. We could talk more in office hours if you want, or you can wait until Wednesday and try it after that. Work on some of the other problems first.
Sounds good. Thank you.
Sure.